Good morning. Today we're going to look at section 2.3 of Pre-Calc 30. We're going to be solving radical equations both graphically as well as algebraically. You have solved radical equations in the past in Pre-Calc 20. Today we're going to focus on the graphic method as much as the algebraic method that you are already familiar with. So to begin with, what we're going to do is take a look at the graph of a radical equation. We're going to find the x-intercepts of that graph, and then we'll talk about how that connects to the roots of the equation. So first and foremost, when you take a look at this equation that they are asking us to work with, what I would like you to notice is that it is an extension of a radical equation. When you look at x plus 2 inside the radical sign with a minus 4, what I'm wanting you to recognize before we graph it using technology is that we see transformations. This 2 on the inside, if I pull it out, is an h value of -2. That means when we go to graph our equation, we should see what used to be a radical equation moving left 2. We have a k value of -4, and that means that we're going to see a graph that is moving down 4 spaces. So when I bring up the graphing calculator, what I'm hoping that I understand is that what used to be this radical x equation is now going to move left 2, down 4 spaces, and then we're going to see it do the same type of thing. And our goal is to find the x-intercepts. That's what our question is asking us to do. So let's take a look at bringing up a graphing calculator. I have started on this already. I have the equation already entered into the calculator. There is that y equals root x plus 2 and the minus 4. When you hit graph, you're going to see again that radical equation that traditionally started at 0, 0, move 2 spaces to the left and down 4. But our goal is to find the x-intercept. And so what I'm going to ask the calculator to do is to find this x-intercept for me. So if I go to second and trace, number 2 is the 0. So if I select that, it's going to ask me to first of all move left of where the x-intercept is. Anywhere over here is fine. We hit enter. We move to the right now, it says, of the x-intercept. We hit enter a second time, and again you can see the little arrowheads point to it. So we're telling the calculator to look for the x-intercept that is in this area, and we'll get that if we hit enter a third time. So it's telling me that the 0 of the function or the x-intercept is at 14 and 0. So if I go back and I just write that the x-intercept is at 14 and 0. Now, what is the significance of this x-intercept? If you go back to the question, the original equation that we just graphed was here. Now, in part B, even though I'm not going to solve it algebraically right now, it's asking us to solve this equation. It looks very much the same. The only difference is that what used to be equal to y is now equal to 0. And so when you look at the x-intercept that we solved, that is what y is 0. So when we find the x-intercept, we're really finding the solution, or the root of the equation is x is equal to the 14, that x value that we were looking for. So I'll come back and I'll solve the equation algebraically so that we can see the steps that we need to go through a little bit later for this one. What I am going to do is move on to a different example here. This time around with this equation, I'm not going to solve it graphically, but I am going to solve it algebraically. And so the steps that I'm going to go through should sound familiar because, as I said, equations that were radicals, that had that variable inside of a radical, you have solved before. So the first step, while it's not necessary in this particular example, is important overall that we isolate the radical. And in this particular equation, the radical is by itself on one side of the equal sign. So the second step that we need to do is to be able to get rid of that radical. We can't work with the terms inside the radical until the radical is gone. So we are going to square both sides. And again, the purpose of that is to to cancel the radical. Because when we square this side where the radical is, the radical being a single term will cancel because of the square. Squares and radicals are opposites. And on the other side where we have two terms, we're going to square them and we're going to get a multiple of terms. So let's just take a look at what this looks like. When I square the square root, they will cancel each other out, and I'm left with just the 6 minus x. On the side where I have the two terms, the 4 minus x being squared, it's much easier to expand it when I see it written as two brackets, two factors. So if I expand that, I'm going to get 16. I have a minus 4x and another minus 4x, which would be negative 8x. And then I have a positive x squared. So I've squared both sides. So what I'm left with is an equation that we have solved before. And we may end up with a variety of different types of equations to solve. And so I'm just going to say solve for x. In this particular question, we have a quadratic. I have the x squared. And so we are going to need to remember how we solve quadratic equations. In Pre-Calc 20, we were learning factoring to solve, quadratic formula to solve. In this particular case, what I am going to do is I'm going to factor it. And what that means, I guess regardless, is I need to move all the terms to one side. And so I'm just going to take a second and I'm going to move all of these terms to the other side so that I have an x squared, I have a negative 7x, and then a positive 10, and that is going to equal 0. And so when I have everything on one side, I'm going to factor it. That means I'm looking for numbers that multiply to my outside numbers, 1 times 10. So I'm multiplying to 10, and I'm adding up to my middle number, which is the negative 7. And that means that a negative 5 and a negative 2 would be the numbers that would do both. And what I use those numbers for when I'm factoring is decomposition. And that's a common method that you may have learned in the past when it comes to factoring these trinomials, breaking up that middle term, and then grouping them 2 and 2. So when you look at the first two terms here, there is a common factor of x, and x minus 5 is left over. These two terms, there is a common factor of negative 2, and x minus 5 is left over when you divide out negative 2 from both. And that means that we have two factors, an x minus 5 and an x minus 2 that equals 0. Now I haven't finished solving for x, I've factored, but remember when you have these factors multiplied to equal 0, that means that either factor or both can equal 0. I better fix this, hang on. X minus 2 equals 0. So when I move the 5 over, I add 5 to both sides, add 2 to both sides, and I have x equals 5 and x is equal to 2. Now with radical equations, there is an issue. We can create what's called an extraneous root. This process of squaring both sides can create an extra answer that is not a correct answer. And so with radical equations, we need to check your solutions always. So if I were to go through and do a check, I'm going back to my original equation. Where is it? 4 minus x equaling that square root of 6 minus x. I'll start with checking the x equals 5. And when you substitute in 5, I often draw a line down from the equal sign just to keep the two sides separate. And I get negative 1 on this side. Square root of 1 is equal to 1. And that means that no, it does not check. X equaling 5 is not a good solution. 5 does not work. So if I check the other solution, x is equal to 2. 4 minus x. And this is the thing with radical equations. There's no guarantee that one answer will always work, that both answers will work. There's times when no answer works. And so we must always check all of our solutions. So substituting the 2 in place of x, I get positive 2 on this side, square root of 4, which is equal to 2, and yes, this one does check. So 2 is a good solution for this radical equation. Now, this equation ended up being quadratic. It is possible that we end up with a linear equation, which requires different steps, but those are things that we need to be prepared for. All right, so we've solved algebraically, we have solved graphically. We'll take a look at a couple of other scenarios here. This question is asking us to solve an equation using 2 different methods, and I'm going to focus on a graphing method here. We've already taken a look at as a single function, and what that means is if I were to solve this equation graphically as a single function, that means that they want us to move all the terms to one side, so that when I subtract the x from both sides and I subtract the 3 from both sides, what we're going to put into the graphing calculator to solve graphically is a single function. And so if this was to be solved graphically, we would do the same type of thing what we did last time, and that would be by finding the X intercepts. Honestly, this is my preferred method of solving graphically, is finding the X intercepts using a single function. But the other method here is equally efficient. It's just a different approach. It says using a system of 2 functions. So what that would mean is that we would end up leaving the 2 sides of the equation. We would create one equation from one side. We would create a second equation from the other side of the original equation. And what we would end up doing in this case is finding the point of intersection instead of the X intercepts. And so I'm just going to show you how to do it this way so that you have a choice as to how you want to solve it when we're solving graphically. So that's one thing, that these are 2 methods, but they are both focusing on solving our equations graphically. All right, I'm going to bring up the graphing calculator. We'll take a look at these 2 equations and what that would look like solving graphically. So I need to clear out my old equation. I'm going to create 2 equations, as I had mentioned. X plus 3 is one equation, and the second equation is the square root of 12 minus 2x squared. And so when we take a look at these 2 equations, I'm just going to hit graph. I'm not too sure if I need to adjust some things, but there is the x plus 3 line. And then we have that equation there. Now I'm going to zoom in a little bit. I can definitely see that they have a point of intersection here, but there is the potential for a point of intersection down here. So let me just zoom in, number 2, and I hit enter. I'm not even seeing enough of my graph. Let me do it using a window. I'm going to make it -3 on the x-axis to +5, and we'll see what we get here. There we go. That might be better. Not so much. I need to go a little bit higher on my y's. I'll go up to 5. Now, even just going through this process might give you an indication as to why I have a preference for one method over the other. It does sometimes take a little bit of adjustment to get to where the The window is going to be correct so I can see the points of intersection. Let's see what the calculator is going to tell me. So I'm going to go second and trace again. Number 5 this time is the point of intersection. So I am going to select number 5. Now I'm going to move closer. It is asking which curve is my first curve, and it is lining up on the first equation I had entered. But I want to get close to this x-intercept. And hopefully maybe it'll tell me about this point of intersection. So is that the second curve? Yes, hit enter and hit enter a third time. And sure enough, there is a point of intersection there. So x being negative 2.4-ish is what I want for the solution. So let me just go back here. We had a point of intersection at negative 2.4, and it was at about a positive 0.5, I believe. Now the y value is not so important. What we want out of this is that x is equal to negative 2.4. There were only x's in our original equation. That's the only value I'm concerned with. So let's go back to the graph and we'll find the other point of intersection over here. So second and trace again, number 5. This time I need to again move closer to where that point of intersection is so the calculator knows which point of intersection I'm curious about. And close enough. First curve, yes, enter. Second curve, yes, no guessing. Enter a third time for it to tell me that the point of intersection is that x is equal to 0.4 and about 3.4. But again, the y value is not the important part. The 0.4 and the 3.4, again, what we're concerned with is the x value of 0.4. These would be the solutions that they are asking us to find. All right, let's try one more and we'll see how this goes. Here's a word problem involving a radical equation. It's about an engineer. There is an equation that we are going to use. It models velocity, which is v in feet per second. D is the distance in feet that it drops with an initial velocity of VO in feet per second and a constant acceleration, which is a. So when we take a look at this equation right away, you can see that, yes, it involves a radical. But for us, a true radical equation is when there's a variable left inside. So what I need to do is go through the information that they've given me in the question. For example, here, it's telling me that the speed of the cars be 120 feet per second. So that would be my velocity. So I'm just going to put 120 in place of v. I'm just going to do this. This is v. The initial velocity of the coaster at the top of the drop is 10 feet per second. So this 10 feet per second is VO. I'll just put that 10 in place of VO. And the only acceleration is due to gravity. So this is our A value. And so we have 2 times 32. And they're questioning what is the vertical drop. And so this is D that we're asked to find. So when you take a look at what we have when we substitute in all of our numbers, yes, we have a radical equation. I'm just going to simplify it a little bit here before we get started. The 100 from squaring the 10, multiplying, we end up with 100 plus 64d in the radical. So again, those steps that we talked about before, isolating the radical is already done for us. That's good to go. Second step, we are squaring both sides. Square this side, squaring this side. 120 squared is going to be 144 with a couple of zeros. Squaring the square root is going to leave us just that 100 plus 64d. Now, when we talked about the third step, that was asking us to solve the equation. This time around, we have a linear equation. And so for us to solve the linear equation, all we need to do is isolate D. And that means I'm moving the 100 over to the other side. And so then if I subtract 100, we're at 14,300 and equaling 64D. So the last thing that I need to do is just divide by 64. That'll get D by itself. And when we do that, we end up with 223.44 approximately. And that is asking us what the vertical drop to the nearest foot would be. And so to the nearest foot, we'd have 223 feet. But keep in mind, this is a radical equation. So before I do anything, I need to make sure that I do a check. So the equation that we were solving was 120 equals 100 plus 64D. Dropping the line down, of course, the 120 on that side. And 100 plus 64 times. Now I'm going to put a few decimal places in. We've already rounded off. And so that's going to make our answer slightly different. It's not going to work out to perfectly 120. But what we end up having is we have the square root of, now I better get my calculator out so that I can check on this. Let me just drag it out. We have the square root of 100 plus 64 times the 223.44, and that works out to be 120.00. So I'm satisfied that this worked out to be about 120.002-ish. To me, that's good enough for a check. And so the vertical drop was 223 feet. So solving our radical equations, again, familiar territory when we're solving them algebraically. Solving them graphically might be the new thing, but we should be comfortable with both. Have a good day.